Gentlemen, may I have your attention, please? I request you first to turn off or keep in the silent mode all the cell phones, and I would also like you to not use your laptops during this session, because we are paying respect to Somesh Bagchi in this session. So I would request you not to use your laptops during this session. I think we should all stand up for a couple of minutes in silence to pay our respect to Somesh Bagchi. The first speaker today in the afternoon session, the first half of the afternoon session, is Rudra Sarkar, who was Somesh's first student, first PhD student, and he will be talking about some aspects of Somesh's work. And I would like to say, before I sit down, that I consider it a great privilege to be asked to chair this session, where we are remembering the work of Somesh Bagchi, and we would then break for coffee, and then the next session would be about reminiscences about Somesh, for which Gadadhar Mishra will be the chair. Thank you very much.
My sincere thanks to the organizers for this wonderful show, and in particular for this session. And for this particular session, I am also thankful to a few key persons who I suspect are behind this plan. But I would not say that it is very wise of them to ask me to give this lecture, because in fact there are quite a few experts in this audience who actually worked in this subject and knows a lot more. Anyway, this is the plan, and for me, S.C. Bagchi was a quintessential teacher. He dedicated most of his professional life for his students in the large sense. A student could be his classroom student, or could be a faculty colleague, or could be anybody, any student of mathematics in any university. So, I would like to dedicate this talk to the students, to the uninitiated, not to the experts. There is this general problem. Suppose V the topological vector space, and tau a collection of continuous linear transformation. Suppose I take a V not equal to 0 belonging to V and construct this space V V equal to span of these elements, taking T from tau and taking this closer. So, V V is a closed subspace of capital V. Suppose it is not whole of it. So, that means V V is a proper subspace of V. Then we ask what elementary elements of V do you expect to be in V V? This is a very vague question. So, I have to make it more concrete with concrete capital V, concrete tau, etc. So, let us see this first example. Take V to be L infinity of R with weak topology and take tau to be the set of translations then we know already Senthil Rani has mentioned this theorem of 1932 by Wiener, which is called Wiener-Stoberian theorem, that e power I lambda x belongs to. So, suppose I take a f not equal to 0 from this V, then V f will contain e power I lambda x for some lambda belonging to R. This is called Wiener-Stoberian theorem. Actually, it says in a different way, but it means that, because suppose V f does not contain e power I lambda x for any lambda, then all of them are outside, then you can find functions say f lambda belonging to L1 of R, which kills the whole of V f and which is does not kill e power I lambda x. Then you look at this bunch of f lambdas for lambda belonging to R, which is a subset in L1 R and which will generate then by translation the whole of L1 R. Okay. But each f lambda kills V f. In other words, f, which is an L infinity function, that will kill all translates of all f lambdas, which is a contradiction, because this space, this generated by the span of translates of this space is the whole of L1 R by Wiener-Stoberian theorem. In 1947, Laura Schwarz proved this following theorem. He took V to be C infinity of R and tau again translations. He used the usual Frechet topology in C infinity R. That means you just get a countable collection of compact sets like this, so that union of k I equal to whole of R. Then you define the seminorms I j of a function f in C infinity R, which is equal to supremum over k I of the jth derivative of f, and this countable seminorm, from this countable seminorm you can get a metric, and that metric will be complete and it will generate a locally convex space, that is called a Frechet space, and that topology we are giving on C infinity R. And with this topology, if you take tau to be the translations, take an f not equal to 0 in V, that means C infinity R, look at V f, the space generated by the translation, span of them and closure. If V f is the whole of C infinity R, then it is meaningless to say, but let us say this. Then V f contains e power I lambda x again for some lambda in C. That is the first part of the theorem, says this. There is a second part which says that suppose V f is not whole of C infinity R, then V f can be characterized by the pairs lambda comma say j belonging to complex numbers cross natural number. That means by the pairs this such that d j dx j of e power I lambda x belongs to V f. That means this f or any function in V f can be approximated by finite linear combinations of such objects. We can call this object lambda comma j. So, any f, this f or any function in V f can be approximated by the linear combinations of objects like this which are in V f. That is the second part of the theorem. See, the translation can be realized as convolution with Dirac delta function. For instance, if I take Dirac delta at a point A, the same as f x minus a, and Dirac delta is a compactly supported distribution. So, we can actually generalize, not generalize, we can rewrite this statement, rewrite the definition of V f, which I said the span of translates of, let us say, a left translation by R closure, but that will be same as, I do not have to write span here, convolution where this is in the dual space of this, which is the same as compactly supported distribution in the closure. These two spaces are same in the closure. So, we can rewrite the definition of V f like this. Pardon me? Yeah, everything with respect to that Fréchet topology, right. In
the E lambda j, why are they different from just taking one of them?
Sorry, so I made a mistake. This is with respect to lambda, not x. Thank you. In 1979, Bagchi with Sitaram proved an analog of this result for rank 1 Riemannian symmetric spaces of non-compact type. Anisha already defined, gave the geometric definition of Riemannian symmetric space of non-compact type X, which is the Riemannian manifold, and for each point P belonging to X, there exists a map, let us call it sigma P, from a neighborhood of P to X. So, the sigma P equal to P, and if gamma is a local geodesic such that gamma 0 equal to P, then sigma P takes gamma t equal to gamma minus t, therefore, it is called geodesic inversion, and that is the definition of a local symmetric space. And when and gamma p is an isometry, and this happens for all the points, and is called a symmetric space, that means global symmetric space when sigma p can be extended to be an isometry for the whole space X. That is the geometric definition of symmetric space, and Ashisha already gave a nice example, rather the characteristic example of Riemannian symmetric space. You take in Rn plus 1 this quadratic structure x1 y1 up to xn yn, but the last one is signature is n comma 1 n plus 1, and then you look at the space X belonging to Rn plus 1 subset such that x comma x equal to minus 1, this is a hyperboloid, it has two seats, you take just one seat, and as you understand that this will automatically give the Riemann structure on the tangent space. So, this is called real hyperbolic space. Now, you can change this quadratic structure from real to complex to get the complex hyperbolic space, or to quaternions to get the quaternionic hyperbolic spaces. So, these are basically the basic examples of Riemannian symmetric spaces. Apart from that, there is one more which is called Cayley upper half plane. So, forget about that for the time being. So, these are the basic examples, but for us we can rely more on a algebraic realization of Riemannian symmetric space. From now on, I will call it ROS, rank 1 symmetric space. So, X is an ROS that can be realized as a quotient space G by K, where G is a semi-simple non-compact connected semi-simple Lie group with finite center. One example we already know, SL2R, and K is a maximal compact subgroup of G. Here in this example, this quadratic structure is preserved by this what is called SON1, and among them I think the south pole will be fixed by SON. Okay. So, this is an example of G by K, and Hn is G by K. So, naturally G will act on x equal to G by K, that means x k will go to G x k when G is acting on it. So, this will give what is called translations on G. Now, as G is acting, the K will also act, and with respect to K action we can define a function f on G, f on x equal to G by K is called radial if f of k x equal to f of x for all x belonging to x and for all k belonging to k. they are I mean just analog of the radial functions on Rn. So, we can have this dictionary like Rn is there, x is there. So, the motion group G SON this k, and then there is SON minus 1 of course, and corresponding group is called M, which is a subgroup of k, which I will use, and SON by SON minus 1 quotiented by SON minus 1 is the sphere Sn minus 1, and here for these rank 1 symmetric spaces k by M is actually diffeomorphic to the Euclidean sphere. We will use these things. Now, let us try to write the statement of Bagchi and Sitaram and then explain the statement. Let f belongs to C infinity x, f not equal to 0. F equal to f is radial. Let V f equal to span is not required. So, dual space of the C infinity functions, that means the compactly supported distribution and with this radial. See, by radial distribution I mean those distributions, those compactly supported distributions which will kill the non-radial part of it, or rather if you act this distribution on an f, on an arbitrary function f, then that will be same with the acting on the radial part of f. So, radial part is the generalization of the even part in one dimension. So, why I am taking radial distribution here? Because I want to stay inside the radial part of C infinity x. Okay. Then they have proved, then there exists lambda belong to C such that phi lambda belongs to V f. I will explain what is phi lambda, and f can be approximated again in the same kind of Frechet topology by phi lambda comma say j x, these functions, that means dj d lambda j of phi lambda x up such that phi lambda j belongs to V f. So, it can be approximated by those phi lambda j which belongs to V f. Okay. Now, let me see, the natural questions are this. Question A, what is phi lambda? Question B, what is its connection with the exponential function? Why you can say that this is an analogous result? So, let me try to explain what is phi lambda. See, now we already have two views about this ROS, Riemannian symmetric space, x and g by k. So, in each view we can explain. For instance, if we look at this g by k, so x is g by k. So, any function on x is a function on g by k. So, any function on g by k is actually a function on g, which is invariant on from the right side, because it is a non-commutative group, left and right sides are different. So, right side by k action. Now, as you know that if you want to do harmonic analysis on groups, then from this exponential functions e power I lambda x, we have to go to the representations. So, we have to look at the representations of g, but not all representations, because we are talking about a subclass of all functions of g, the functions which are invariant under the right action of k. So, for these functions one can show that only these representations which are parameterized by C, which are called class 1 principal series representation, will be important. So, there is a theorem called Frobenius reciprocity theorem, which can be used to show the if you take any other representation of g, so that will kill any function which is defined over x, that means which is invariant under the k action. Now, representations are actually equivalence classes, but if we look at one realization of this pi lambda, then the carrier space of pi lambda can be taken as L2 k by m. Remember, this k by m is something like sphere, and in L2 k by m, starting from E0, E0 is the constant function 1 on k, we can have an orthonormal basis, countable orthonormal basis, and this is an infinite dimensional representation. Of course, it is a non-commutative group. Apart from the trivial representations, most of the representations are infinite dimensional. So, we have to look at the matrix coefficients of the representation. See, if I look at this matrix coefficient, where the first element of this O and B I have taken, then this is equal to phi lambda x. Why this is important? Because I am dealing with, in the theorem of Bagchi and Sitaram, we are dealing with radial functions, and we can show that for radial functions, if we integrate with respect to any other matrix coefficient other than this, then the other matrix coefficients will annihilate the radial functions. This follows from what is called Schur's orthogonality relation. So, when we are dealing with this radial functions, we are suppose this matrix coefficient is important, and that is playing the role of e power I lambda x in a sense, because e power I lambda x from the point of view of representation theory is one dimensional representation. It itself is its matrix coefficient. That is what we used to get. Here we are getting exactly the same thing. Now, if we want to take more geometric viewpoint, then I can just report that just like e power I lambda x, phi lambda is also an eigenfunction of the Laplace operator. In any Riemannian manifold corresponding to the Riemannian structure, we can have a Laplacian, that is called Laplace-Beltrami operator, and phi lambda x is also an eigenfunction. Okay, where rho is a positive real number here, that I will not explain, I do not have time to. Okay. But this means this is the inner product of L2 k by m. So, I can write this out in integration. So, that will involve the actual action of pi lambda. Then this will be, this will look like